So we will start today with a slightly new topic, which is the first of the partial differential equations of physics, the famous partial differential equations of traditional physics, and this is Laplace's equation, and of course if you have a term on the right hand side it is Poisson's equation. So the equation we have in mind is of the form del squared some function of r equal to some other given function of r. Okay. This is Poisson's equation. Okay. By the way, the operator del squared itself appears in all these equations, all the standard equations we are going to discuss namely Poisson's equation, the wave equation, the diffusion equation, the Helmholtz equation and so on. And there is a reason for it, of course, because del squared is a scalar operator, it is invariant under rotations, and these physical systems or situations that we are going to describe would generally have rotational invariance of some kind. So you have a second order differential operator del squared, which is a scalar operator, has a lot of fantastic properties. It is called an elliptic partial differential operator in the classification of such operators, and it is absolutely fundamental. When you generalize this del squared to higher dimensional spaces, curved spaces, other manifolds and so on, it turns out that if you know a certain eigenvalue problem based on the del squared, namely very roughly speaking, if you know its eigenfunctions and its eigenvalue spectrum, then you can say a great deal about the underlying space itself. So it is a very interesting fact that knowledge of the eigenvalue spectrum of the Laplacian operator and its generalizations gives you a great deal of information about the underlying space itself. Okay. I will come back to this point later on. For the moment we will focus on Poisson's equation, the first of these equations, okay. And the question is, how do we solve such a linear partial differential equation where you are given some function g of r. So we will do this by a sort of combination of physical arguments and mathematics in a very simple way. All of you are familiar with this equation from the most classic example of all, namely electrostatics, where you have del squared acting on the electrostatic potential is equal to the charge density on the right hand side apart from a constant factor, and we know what the solution to that is, essentially Coulomb's law plus the superposition principle, that is the general solution. So we are going to exploit that fact, and I will give a physical argument to see how you can extend the solutions of this equation to higher dimensions and so on. But the purpose here is restricted. For all these partial differential equations, my primary aim is to find the so called fundamental solution to this equation, namely the fundamental green function for such operators, differential operators, which will then help you to write down the solution for the general inhomogeneous equation. So we would like to find the green function for the del squared operator. Now what is the green function? Just to recall to you, since you must have already come across this in courses on differential equations, the idea behind a green function is the following. So let us start with the simplest example, namely a single real variable. So you have a function f of x and you have some differential operator d which involves x, functions of x, derivatives with respect to x and so on and so forth, acting on this f of x is equal to some other function g of x on the right hand side, a given function here. And the question asked is, what is the solution to such an equation, an inhomogeneous equation? Okay. The answer is of course that you need to formally invert this operator and somehow get it to act on this g here. So let us do this in abstract notation and see what it looks like. In abstract notation, if this d is a representative of some operator d in some space, some linear space, and this f is represented by this ket vector on the space, I will use Dirac notation here, this is equal to g on the right hand side. This will imply formally that the solution f is equal to d inverse if it exists acting on g, formally of course, but that is not all, because you could also have a piece plus a piece which is some vector h hi, where d acting on this hi equal to 0, and in fact you must sum over linear combinations of all such eigenfunctions or eigenstates such that if this operator acts on it, it annihilates it, you get 0 here. So as you can see, this is the solution of the homogeneous equation, d of x acting on some h of x is 0, and this is the part that comes from the inhomogeneous equation here. And in the language of differential equations, this portion, when you write it back in function space, this portion is what you would call the particular integral, and the rest of it you would call the complementary function. Now of course we can write this back in the position space and see what happens here. Well, remember that this so called f of x is nothing but the representative of this ket vector in the x basis, if you like, it stands for that. Then what does this equation really look like? It says f of x equal to, and there is some operator g acting on d inverse acting on this g, and now we can ask in very naive terms, we can see what it is going to be. This is a differential operator of some kind, so the inverse of it in general would be an integral operator in general. So this thing would be of the form an integral over dx prime some g of x comma x prime little g of x prime plus of course a summation ci hi of x, where these are the representatives in this basis x basis of these abstract vectors in function space. So this g here represents this d inverse. In fact we can make it even more precise. What is this g of x comma x prime? The so called green function for this differential operator. This thing here is nothing but x d inverse x prime. It is obvious from this notation that that is precisely what it is. Okay. I leave you to figure this out. I mean it is very trivial. Do you want me to do this? See how it is done? Or? Put an x on either side, so you get x f, that is equal to f of x, that is equal to x, and then there is a d inverse g plus summation over I ci x h sub I. This is what we have called hi of x. Okay. So that is what this thing is, and here now insert a complete set of states, and a complete set of states is integral dx prime x prime x prime. Okay. That is the identity operator. I insert it in between, and then of course I get x d inverse x prime, that is a function of x and x prime which we have called g, the green function, integrated over dx prime, and then x prime acting on g, that is g of x prime out here. So this is all it is. This is writing it down, this abstract notation is trivial, writing it down here is just one more step. Take the matrix element between x and x prime and that is it. Okay. This, yes.
Do we have to worry about whether d inverse exists or not?
Yeah, we have to certainly worry about d inverse exists. So if it exists, then this is true. So we will have to ask what are the conditions under which these d inverse exists, etc. And what I am going to do a little later when we talk about integral equations is to show you under what conditions you would have this inverse exist for this operator. For the moment we assume it exists. We go. So this thing here is called the green function of the differential operator dx. It is nothing but the inverse of the operator expressed in this basis, nothing more than that. And we need now to find out what this g is, but that is very simple. We need an equation for this g, that is not hard to find, because notice that d inverse must be equal to the identity operator. Okay. And if I express this in the position basis, what is going to happen? This thing here is represented by dx, and this guy here is g of x comma x prime, and that is equal to the bra of x with the ket of x prime, which is nothing but delta of x minus x prime. So solve this equation with a delta function on the right hand side, and then you can solve this general equation by plugging that in here and then doing this integral. It gives you the particular integral. Okay. So this in a sense is the green function method. All you are doing is to invert some operator, writing it in some particular representation, and it satisfies this differential equation, and engineers are used to calling this the unit impulse function or whatever it is. You solve it and then you superpose all such responses to the unit impulse function multiplied by whatever you have there in the given function, and you have your solution. Okay. Now how does this work in practice? Well, if you look at a very simple example, let us look at, just for to refresh your memory, let us look at an extremely simple example. Oh, first one question I should ask, however, how much of this should you put in? What decides that? Yeah, all the boundary conditions will decide what these coefficients are and what the admixture of the complementary function is to the particular integral, as we will see now from a simple example. So let us do this example first and then come back to Poisson's equation. Oh, the example is a standard one. It starts with a self-adjoint differential operator, so it is of the form d2f over dx2, this is f of x, equal to some given function g of x. I would like to solve this equation. Okay. This is the simplest of examples. We need some boundary conditions and we need to say what is the range of x, etc. So let us take the unit interval, let us say x is an element of 0, 1, and I need to put some boundary conditions on this f. Okay. So typically you would say f of 0 equal to something or the other, f of 1 equal to something or the other, some constant, some other constant. Okay. Call this a, call this b. So subject to these boundary conditions, the question is what is the solution to this differential equation, what is the particular integral here. So let us try to find out what the green function of this operator is, and the green function satisfies d2g over dx g dx2 equal to delta of x minus x prime in this form. Okay. So what it says is that the second derivative of this with respect to x is essentially 0 except when x equal to x prime. So it is a big jump, a delta function jump at x equal to x prime. So let us first solve it in the region x less than x prime, and then we solve it in the region x greater than x prime. So 0 less than equal to x less than x prime. What is the solution to this equation? Well, this is 0 here. So it says the second derivative of this g as a function of x with respect to x is 0, which means that g is just a linear function, right. So this is equal to, this implies that g of x comma x prime equal to some a1x plus a2. a1 and a2 could depend on x prime, in fact they would in general depend on x prime because we just integrated with respect to x alone. And in the other region, x prime less than x less than equal to 1, g of x comma x prime equal to some other constant a3x plus a4. Okay. And now we have 4 constants to be determined to give us the full g, and what are the pieces of information we have? Well, the first piece is this out here. So we put in the boundary conditions. I need to put in this boundary condition here too, okay, and then there are 2 other pieces of information needed to determine what the constants are. And what are those pieces of information? What would it be? Well, the first one is the continuity of g. Okay. The reason I assert that g is continuous is because its second derivative has a delta function jump. Okay. So what does it mean for the first derivative? This has got an infinite jump out here. So what does it mean for the first derivative? It means the first derivative has a finite jump of some kind, right, because if you integrate this equation, with respect to x from some, for a fixed x prime, say x prime minus epsilon to x prime plus epsilon, you integrate dx and you integrate this guy here, then it says d2g over dx2, this is equal to dg over dx at x prime plus epsilon minus dg over dx at x prime minus epsilon. Immediately to the left of x prime and the right of x prime, I integrate over a small range, okay, and I get this. And what is this equal to? I integrate this across the point x prime in x. So what is the answer? What happens if you integrate a delta function? You get 1. So this is equal to 1. So in a sense it says that the discontinuity of the first derivative of g at the point x prime is given to you. Okay. So you need to use that information here. I differentiate both sides with respect to x and put x prime, x equal to x prime minus epsilon on the one hand plus epsilon on the other, and take the difference between the two. For the minus I take this, and for the plus I take that, and I equate the two at x prime. So that gives you one more condition. And what is the last condition of all? This says that the derivative of g has a finite jump. So what does g itself have to have? It has to be a cusp, because it has to be something like this, because the slopes are different and there is a finite difference between the two slopes. So the function g itself will look like this, g prime will look like this, and g double prime will have a delta function jump at that point. Okay. So whenever you have a delta function here in the second derivative, you know immediately that the function itself would be continuous. But the first derivative has a known jump. So that fixes all the conditions. The first one is fixed by f at 0, then f at the other end at 1, then the continuity of g at the point x prime will give you one more condition between the 4 constants, 4 quantities a1, a2, a3, a4, and the finite jump here gives you one more condition. So you can put those in and work out what a1, a2, a3 and a4 are, and that is your green function. You can do this for more general boundary conditions. The most general condition would be f of 0 plus some multiple of f prime of 0 is something else, and similarly for 1. These would be mixed boundary conditions both sides, and you can write down the green function in the general case. Okay. So this gives you some idea of how you handle the green function method. Okay. What we would like to do is a slightly simpler problem in some sense. We would like to do it for higher dimensions, certainly we are looking at partial differential operators, but we would like to get the fundamental solution. So in general the boundary condition I am going to take is going to be the green function simply vanishing at infinity or something like that. So we will take all of space and ask what happens if the green function vanishes at infinity. So now let us go back and look at Poisson's equation. We will write the solution down by guesswork and then we try to derive it with more sensible considerations. So if you recall, this equation phi of r is minus rho of r over epsilon naught. If you recall what the solution to this equation is, this Poisson's equation in electrostatics, what is the solution to it? It is essentially Coulomb's law, right. The solution is phi of r equal to minus an integral d3 r prime rho of r prime over modulus r minus r prime 1 over 4 pi epsilon naught, right. That is the solution, it is Coulomb's law, and then the superposition principle is used to add up the potentials due to all the charges, all points where the charges. Okay. Now what does that imply for the general equation? Well, the general equation was of the form f of r, this was equal to some g of r on this side. By analogy with this, it is clear that the solution we are looking at is f of r is minus 1 over 4 pi g of r prime over this. So the green function in this problem for the del squared operator is nothing but minus 1 over 4 pi mod r minus r prime. That is the green function, and we should get this, we should be able to derive this rigorously, that this is indeed the green function for the 3-dimensional del squared operator, satisfying the boundary condition that this solution, by the way, for Poisson's equation is written down assuming that the potential vanishes at infinity. So the boundary condition on this G is that as r goes to infinity, this G vanishes, this whole thing. So this is the free green function with natural boundary conditions, and now let us see how to derive this. So we will start with this equation and write the particular integral. This implies that f of r is equal to an integral d3 r prime g of r comma r prime little g of r prime plus of course the complementary function, but I am not interested in it at the moment. I just want to know what the green function is. And what equation does this G satisfy? It satisfies the same equation as here with a delta function on the right hand side. So you have del squared G of r prime is equal to a delta function, a 3-dimensional delta function of r minus r prime in this case. I need to solve this equation, put the solution back in here, and then that is it, that is the particular integral. Okay. Now just to remind myself that the derivative or del squared is with respect to r, let me just put an r here to show that it is with respect to the variable r, the vector r, rather than r prime. Okay. Now I assert that this equation here implies immediately that this G is a function of r minus r prime and not r alone. And the reason I do that is because the right hand side is a function of r minus r prime. Del squared, del itself, the derivative with respect to r is the same as the derivative with respect to r minus r prime. For every fixed r prime it is just a shift. Are these two statements enough to say that the solution will also be a function of only r minus r prime? Are these enough? Del squared is invariant. Del squared. So if I put r equal to r minus r prime, so let this be true, then my statement is del r squared is the same as del r squared. It is just a shift. So this guy could be written del capital R, this is delta 3 of capital R vector. So can I now assert that this also is a function of capital R vector? Can I do that? Think of the example we looked at a little earlier, d2f over dx2 equal to the right hand side was again a delta of x minus x prime for the second derivative operator, but that green function did not turn out to be, we did not work it out fully, but it is not a function of x minus x prime. Why not? The d2 over dx2 was also d2 over dx minus x prime, the second derivative. The delta of x minus x prime, a function of x minus x prime, and yet the green function did not turn out to be a function of x minus x prime. What happened? Yeah, finite boundaries. The boundary condition broke this translational invariance. The boundary condition broke it. So you can't shift arbitrarily because there are finite boundaries. In this problem, however, we are asking for a solution as this vector goes to infinity, we are asking for something which goes to 0, right. So as r goes to infinity, r minus r prime also goes to infinity for every fixed r prime. So in this problem with these natural boundary conditions, the boundary condition is also translation invariant. The operator is translation invariant, the inhomogeneous term is translation invariant, and so is the boundary condition. So we can assert therefore that the solution is also translation invariant. So this will imply now that the equation we have to solve So we have to be careful therefore. So the equation we have to solve is del r squared g of r equal to delta 3 of r. That is the equation we have to solve. What should we do? We should do something which converts this del squared into a multiplication, and the obvious thing to do is to do the Fourier transform immediately. So let us define a Fourier transform g of r equal to, it is in 3 dimensions, so it is 1 over 2 pi cubed d3k e to the power I k dot r g tilde of k. Okay. And of course there is the inverse relation. This will also imply that g tilde of k equal to integral d3 r e to the minus I k dot r g of r. Okay. And let us put that in here. Let us substitute this representation for g in here, and the del r does not act on that, it acts only on this. Now what does del do when it acts on the scalar e to the I k dot r? What does that do? It just brings down an I k vector. All it does is bring down an I k vector. This is a plane wave. This guy represents a plane wave. The normal to the wave plane is the k direction, and the del always acts is always in the direction of the maximum rate of increase. So this is I k. So what is del squared? Del dot this guy. So we got to do the divergence of this, but this is not dependent on r, and you get only the divergence of only the gradient of this once again. So it says del squared is minus or whatever it is. So let us put that in right away. So this says 1 over 2 pi whole cubed integral d3k e to the I k dot r minus k squared g tilde of k is equal to, on the right hand side, the delta function, but we can write the delta function itself in terms of this exponential, right? The delta function's Fourier transform is just 1, so you can write this as 1 over 2 pi whole cubed integral d3k e to the I k dot r. And this forms a complete set of states for all k integrated over k. It forms a complete set of states in the R space, and you are equating these two guys here. So component by component they must be equal. When you equate two vectors, they are equal component by component. So the coefficient of each I to the I k dot r on the two sides must be equal, which says minus k squared g tilde of k must be equal to unity. Okay. So we have got g tilde of k, it is minus 1 over k squared, that is it. So it immediately says that this solution, yes.
What happened to the k squared g tilde k, I mean equal to just d cube?
This quantity is equal to that.
This you are expressing whole the integral, and there is on the LHS k squared g tilde.
So del squared on this gave you this minus k squared, and then there is a g tilde of k.
And then
and I wrote this is the delta function. This is the 3-dimensional delta function. So if I move this to the left hand side, it says this minus 1 is equal to 0. So it says a certain vector, a certain function is 0 identically. And when is a vector 0? When every component is 0. And what are the unit vectors in this problem? E to the I k dot r's. in function space they are the unit vectors, and for every k this quantity must be 0. Okay. That says g tilde of k is minus 1 over k squared. Okay. So the argument is completely rigorous, but it has to go you have to go through it, and the reason you can equate Fourier coefficients is because these things form a complete set of states, and therefore you can bring everything to the left hand side and say a certain vector is 0, which means every component is 0. So each Fourier component must be 0, and therefore once I put that in here, this is minus 1 over 2 pi whole cubed integral d3k e to the I k dot r over k squared, that is g of r. If I can evaluate that integral, then I have got an expression for g of r. I put that back in the g of r comma r prime, and that is it. That gives me the fundamental green function. So let us see how to do this integral. What would you do to tackle such an integral? If you took an arbitrary coordinate system, you are in deep trouble, because this means k vector points somewhere and you have to integrate over all directions in k, the r vector points somewhere else, you have got to integrate over all the angle between the two, because e to the I k dot r has e to the I modulus k modulus r, the cosine of the angle between them, and that is a big nuisance. That is a terrible nuisance. It is not trivial to do this integral at all if you are going to do it the hard way, because if you take two arbitrary vectors, if you took some vector like this and some other vector like that, this has got some polar coordinates r theta phi say, and this has got r prime theta prime phi prime etc. We are asking for the angle between these two guys, the dihedral angle between these two vectors, this direction. You can rewrite that, you can write this angle in terms of the polar coordinates, the polar angles for each individual vector, right. It is called the law of sines or some such thing. It is a standard problem in spherical trigonometry. I do not know if that is learned by people, but if the coordinates here are theta phi and the polar coordinates here are theta prime phi prime, and this angle is gamma, then there is a relation which is essentially the addition theorem for the Legendre function of order 1. So it says something like cos gamma equal to cos theta prime plus sine theta prime cos phi minus phi prime. So you have to put that in here and then integrate over theta prime and phi prime, which is a terrible job, it is horrible. So that is not the way to do it. You could ask, can I do it in Cartesian coordinates? Well, you could in general, except that you have this factor sitting here. Otherwise this itself will be a product, so you could do this in Cartesian coordinates, but doing it with this k squared is again a big problem. So what should we do? What should we do? We should clearly look at some invariance of this quantity here, this g of r. It is a scalar, and the fact that it is a scalar means it is invariant under rotations. So you could actually choose your coordinate system as you please. You can choose the polar axis of your coordinate system as you please, and given any other choice you can bring it to this choice by a change of variables in the k space. Now what is this, what is the vector that is sticking out? K is integrated over, so what vector is sticking out? R vector. So let me choose the polar axis in k space along this vector r. You can do that. You can always do that. So once I do that, then the polar angle of k is just cos theta, there is just a theta, and e to the I k dot r becomes e to the I k r cos theta. Is there a phi dependence? No, so I can integrate over phi, and what does the integral over phi give you? Gives you a 2 pi. So this immediately means that you can in k space choose this axis along the direction of r, and then k is integrated over all directions, but this angle is theta here, and this is a typical k. So this integral becomes g of r equal to, by the way I said that this function is a scalar, so I really expect it not to depend on the direction of r either. It should finally end up depending only on the magnitude of this r, right. So I could write g of capital R without the vector sign, but let us see if that really comes out or not. So this is equal to minus 1 over 2 pi whole cube integral zero to infinity k squared dk, but there is a k squared in the denominator which obligingly cancels out, and then there is a 2 pi from the phi integral, so this becomes a 2 pi squared, and I have done the pi integral on the phi integral now, and then I have an integral over the theta which is minus 1 to 1 d cos theta e to the I k r cos theta. Okay. I change variable to cos theta, it is running from minus 1 to 1. So this thing gives you e to the I k r minus e to the minus I k r over I k r, but the numerator is 2i sine k r. So I get rid of this and write this as 2i sine k r over I k r. So this is 4 pi squared, let us make it a minus 1 over 4 pi, and there is a 2, so this is a 2 pi squared. The 2 cancels, the I cancels. By the way, the k squared cancels, the r comes out, and you have dk sine k r over k. So this is equal to minus 1 over 2 pi squared capital R integral 0 to infinity dk sine k r over k. That is it. But this is the Dirichlet integral, capital R is positive. So what is the value of this integral? Pi over 2. So this gives you so you have the Coulomb potential back again with the 4 pi's and the sine and so on. So in a sense what this del squared is telling you is that the del squared phi, the electrostatic potential giving you the charge density on the right hand side, this is not an accident. Coulomb's law is directly a consequence of the fact that the operator is del squared. So very often you see the statement that the Green function for del squared is just the Coulomb potential. In fact you could define the Coulomb potential in an arbitrary number of dimensions as the inverse Fourier transform of 1 over k squared, or as the Green function, free Green function of the del squared operator. We will do that very shortly, but I want you to see how this 1 over r minus r prime modulus has emerged. Okay. And the rest of course follows. Now you can write f of r equal to minus 1 over 4 pi integral d3 r prime g of r prime over mod r minus r prime. Okay. Plus of course the complementary function, but I took the boundary condition that this went to 0 at infinity, and then this is the solution here. Okay. Now of course you can look at various special cases. You could ask what happens if this is a function only of magnitude, if it is a charge density for example, what happens if it is a spherically symmetrical charge density, so it depends only on the vector, the magnitude of the vector r prime, and so on. All these cases can be looked at, and all of you I am sure are familiar with the fact that this quantity here 1 over mod r minus r prime is called the Coulomb kernel for obvious reasons, and you normally, when you do these multipole expansions, you expand this guy in powers of r over r prime or something like that. And what does that series look like? Well, there is a famous series which goes like summation L equal to 0 to infinity. If the angle between r and r prime, so the angle r prime equal to gamma, say, if the angle between them is some gamma, then this expansion here says it depends on whether r is bigger than r prime or r is less than r prime, and the expansion generally goes like this is equal to 1 over r, the greater of the two, and then r prime over r to the power L, and there is a PL of cos theta, cos gamma. But if I want to write this in terms of the polar coordinates of the r and r prime separately, then I get the spherical harmonic expansion of the Coulomb kernel, which again I am sure is well known to you from electromagnetism. You have to really write this cos gamma back in terms of cos theta prime plus sine theta prime, etc., and use the addition theorem for the Legendre polynomials. And this expansion would look something like summation, I am not sure about the factors, but L equal to 0 to infinity, this part would be the same, r greater, r smaller over r greater to the power L, and then there would be pieces which would look like there is also a summation from m equal to minus L to L, there would be y Lm of theta phi, y Lm star of theta prime phi prime, and so on, some such thing, some 2L plus 1 factors and so on, depending on how this is normalized. These are the spherical harmonics. So that's this gives you the multipole expansion in general for this Coulomb potential, but this is true in general for any 1 over mod r minus r prime. Okay.